Viral headlines about an impending internet apocalypse have been circulating recently, fueled by the fact that we are currently navigating the active peak of solar cycle 25. Let's look at the science. A solar storm will not cause the Earth to explode, it won't strip away our atmosphere, and it will not physically harm human bodies on the ground. The actual threat is a product of our own engineering. Modern civilization relies on a highly sensitive, deeply interconnected web of long-distance electricity grids, orbital satellites, and global communications. A massive solar storm targets this digital and electrical nervous system with catastrophic precision, threatening to crash the networks we depend on while leaving the physical planet unscathed. The term Internet Apocalypse stems from a 2021 research paper by computer scientist Sangeeta Abdou-Jyoti. Her work highlighted a specific, under-researched vulnerability at the bottom of the ocean, the massive undersea fiber optic cables that connect our continents. While the fiber optic glass inside these cables is immune to magnetic storms, the electronic repeaters spaced along the line are not. These signal boosters are highly vulnerable to the geomagnetically induced currents that a severe solar storm generates. If those repeaters fail, North America, Europe, and Asia are suddenly digitally severed from one another. International banking, global supply chains, and overseas cloud servers would go dark instantly, costing the U.S. economy alone an estimated $11 billion every single day. Because a massive storm could cause trillions of dollars in damage to this infrastructure, space agencies around the world treat solar monitoring with extreme urgency. To understand how to protect ourselves, we look 93 million miles away. The sun is a churning ball of plasma and complex, twisting magnetic loops. When those magnetic loops twist too tightly, they snap. That snap hurls billions of tons of magnetized solar plasma, a coronal mass ejection, into space. We catch these eruptions the moment they happen, using high-definition solar watchdogs like NASA's SDO and SOHO satellites. They stare directly at the sun, capturing the speed and trajectory of the expanding plasma cloud to see if it's Earth-directed. If the cloud is headed our way, it still has a long way to travel. That's why we place early warning satellites about 1 million miles away at a location called Lagrange Point 1, or L1. At this gravitational sweet spot, a spacecraft can hover in place directly between the Earth and the Sun. Observatories placed at this vantage point, like India's Aditya L1 spacecraft, carry specialized payloads. They directly measure the plasma and magnetic fields of the passing cloud before it reaches our atmosphere. By sitting upstream in the solar wind, these satellites act as cosmic tsunami buoys. When the wave hits, they give Earth a vital 15 to 45-minute warning window to prepare. Down here on Earth, we have our own natural defense system. Deep inside the planet, churning liquid iron generates a massive magnetic shield called the Magnetosphere, deflecting the everyday stream of charged particles from the sun around the planet. But a coronal mass ejection is much denser and faster. When it arrives, its danger level depends entirely on the direction of its own magnetic field. If the incoming field points north, it aligns with Earth's magnetic field. The two fields essentially repel each other, and the storm mostly bounces off or slides around us. If the field points south, opposite poles attract. The southward field of the CME violently connects with the northward field of the Earth in a process called magnetic reconnection, peeling open our protective shield at the front. Those broken field lines are swept behind the planet before snapping back together like stretched rubber bands, accelerating highly charged particles straight down toward the north and south poles. This southward magnetic interaction turns a passing plasma wave into a direct, violent injection of solar energy into our atmosphere. Once accelerated, those highly energetic solar electrons hurtle rapidly down the invisible magnetic funnel lines directly into Earth's upper atmosphere. When they hit, we get atomic excitation. Solar electrons smash into oxygen and nitrogen atoms, bumping the atom's electrons into unstable energy states. As those electrons drop back down to their original energy level, they release that extra energy as a photon. The resulting colors are a chemical fingerprint of our atmosphere. Green is produced by oxygen, while blue and purple come from nitrogen lower down. This glow represents the visible exhaust of Earth's magnetic field, actively fighting off a solar storm. But the physics doesn't stop in the sky. As the magnetic field violently shakes, it induces massive electrical currents in the ground. These currents seek out the easiest path they can find, our power lines and oil pipelines. In a worst-case scenario, like the Carrington event of 1859, these voltage surges can cause custom-built grid transformers to overheat and melt. Because these massive transformers take months to manufacture, the resulting blackouts could last weeks or even months. This is why operational centers like NOAA's Space Weather Prediction Center monitor these threats around the clock. They use specific G, S, and R scales to rank the severity of geomagnetic storms, radiation hazards, and radio blackouts. When an extreme warning is issued, grid operators deploy their ultimate failsafe. They use that 45-minute warning window to intentionally trigger temporary rolling blackouts, decoupling sensitive transformers to save them from melting. We cannot stop the sun's magnetic temper tantrums, but by treating space weather with the same urgency as terrestrial hurricanes, we can engineer the failsafes required to survive them.